Let's get her going. Welcome, everyone, and thank you for joining today's Insulectro virtual OEM forum entitled The Heat is On, Finding PCB Materials That Like It Hot. My name is Ron Murdoch, Insulectro Technical Account Manager, and once again, your gracious host for today's OEM forum. Our world is a world of constant change. Innovations in technology are advancing on an exponential scale. New ideas drive innovations and new applications for PCBs. Sometimes such innovations take PCBs to uncharted and uncertain environments where they must live and survive reliably for a long time. An example of such an advancing technology is the electric vehicle market. EV's advancements and innovation push material companies to keep pace, while companies like Isola are already in lockstep. Isola's trademark, the base for innovation, epitomizes their commitment to providing material solutions for the world's premier technologies for today and tomorrow. Today, our subject matter experts will answer the many material questions about what's cooking under the hood and other market segments that put thermal performance and thermal reliability center stage. The heat is on. Listen in and learn about the challenges designers face when solving their triangles and getting Rev 1 right. Designs and applications in extreme environments present many challenges that we will explore today. Please use the Q&A feature at the bottom of your screen to ask questions, and we will get to them at the end of the presentation. Also, past OEM forums can be found on the Insulectro website, www.insulectro.com. Now, in the spirit of always learning, please join me in welcoming our subject matter experts for today's OEM forum. First, Insulectro's very own Vice President of Technology, Chris Hunrath. Chris will be our guide as he leads the conversation with our distinguished Isola guests on today's topic. Now, introducing our distinguished guests and SMEs, please welcome Michael Gay, Isola's Director of High Performance Products, and Steven Sakanina, Isola's Director of High Speed Digital Products. Michael and Steve's vast experience and expertise will certainly be informative and educational. And now, Chris Hunrath.
Thanks, Ron. So this is a slide we use in all our presentations, and really, I think it kind of explains what we're trying to accomplish here. PCB and electronics are becoming very material science intensive, and what our goal is here with these kinds of webinars is to have the OEMs have higher success rate in their design efforts. So again, the goal is for Rev 1 to work. Rev 1 doesn't always work, but we're trying to increase the success rate of that. So, some of it comes from the materials, some of it comes from the stack up, the design, all these other attributes. But really our goal here is to try and link all these things together so, there's a higher degree of success. So Ron talked a little bit about, underhood, and you're going to hear a lot about that today. Some of the things that are driving, new materials. Classically we've been dealing with things like epoxy and polyimide for PCBs. Of course, with the low loss materials, we've seen the rise of, first it was the cyanide ester blends, but now more commonly we see the PPO, PPE systems. The system that we're going to talk about today is very different than those. And it fills some performance areas that aren't being covered today. So with that, I'm going to turn it over to Steve. Let him talk a little bit about the design basics and what we're looking for in material in this space.
Right. So for some of these electric vehicles, we're going to be looking at talking about designing for battery packs with lithium-ion cells at 400 volts. Commercial vehicles, that could run up to 850 volts, AC/DC converter chargers, battery packs, and all sorts of DC/AC inverters that drives e-motors, as well as DC converters for high voltage batteries. And if you look at the chart on the right of this slide, this is a chart that just shows the rise of electric cars. And it's predicted by 2022 that electric vehicles will cost the same as their internal combustion counterparts. And, we really think that'll be the liftoff point for sales. And if you look, this is a market that's just predicted to explode. Here you see it going all the way out to 2040. But really it's an explosion, and Bloomberg is predicting 450 million EVs cumulative in the next 19 years. So that's pretty impressive. And again, the focus here is all that voltage and all that heat. So we got the engine at 428 degrees Fahrenheit.
So electric vehicles have different demands than regular combustion engines or combustion vehicles do. So they have some different needs, and again, that's why there's a need for new material in this space. So, Mike, tell us a little bit about the material demands for EV vehicles.
Thank you, Chris. One of the biggest issues that we're seeing in the industry today is how do you handle these very high voltages with these high power requirements that are needed for vehicle charging and for moving a lot of energy from one location to another. And so what we run into is thermal issues where you have thermal reliability due to the cycling of the product, as well as the voltages that drive CAF performance issues. And so this material is well suited for handling both the thermal and the CAF performance requirements. And we'll cover some of that in the next upcoming slides. The temperatures, obviously, they're going to increase with this high energy in the board. We've seen temperatures up to 160 degrees C, and there's discussions of all the way up to 200 degrees C during operation in a cyclic manner. So the material has to be able to handle those temperature cycles as well as peak temperature operating conditions on the vehicles and in the systems that are charging these vehicles. So that means you need increased thermal conductivity to be able to move the heat out of the board so the heat doesn't remain in the board. And then one of the goals was to try to reduce the overall weight of the board versus the ceramic PCB. So, and then finally, cost mitigation. Obviously, automotive, they are very cost sensitive. So we need something that's inexpensive that people can purchase and use in their operations, in the operation of the vehicle.
Yeah, so underhood applications cycle and temperature, just like aircraft composites. A lot of those applications cycle and temperature. We see cycling and temperature in regular PCBs also, but not to the extremes you'd see in an electric vehicle. So, Steve, tell us a little bit about some of the testing you guys have done on this for qualification.
Yeah, thanks, Chris. So some of the long-term high temperature operation testing includes testing at 200 C for 2,500 hours. We've done high voltage CAF resistance testing for 1,000 hours at 1,500 volts, and high temperature storage at 200 C for 2,500 hours. And then temperature cycling. So we've done several different iterations of that, but we've done testing at negative 40 C to plus 175 C for 1,500 cycles, and thermal conductivity testing at 300 amps. So anyone who's familiar with some of the testing that has been typically used with printed circuit board materials in the past with traditional epoxy materials, some of these numbers here, they're just off the charts. In typical applications, for example, you'd be talking about a CAF test, you might be talking about 100 volts. We're talking about 1,500 volts. So these numbers are really off the charts, but this is the kind of demanding, harsh environment that is required for high voltage.
I can tell you most FR4s, epoxy-based FR4s, at 2,500 hours at 200 C would be pretty dark in color after that amount of time at that temperature.
Yep.
So I'm familiar with ceramic, PCBs. I don't know if folks on this call are aware, but Insulectro supplies the ink, the sintering inks, and some substrate materials like green tape, which sinter at 850 Celsius. And they have their applications because there are certain environments where you have to use a ceramic material. You can't use an organic material. But there's a big space that's not being filled, that it's not suitable for FR4. Used to be kind of the domain of polyimide, but there's a need for something new, and that's what this is all about. So Mike, talk a little bit about some of the other things that are needed in you know, in the structure in some of these boards for electric vehicles and other systems. Did we lose Mike?
I muted. Sorry about that.
Okay.
So obviously the high temperature operating conditions that these vehicles are going to see, either exposed to the environment near some of the battery packs or in some of the components that are in the vehicle, and so to be able to handle those temperatures, you need things like copper coins or various heavy copper features within the board that are going to draw that energy out of the board and pass that to the environment. And so when you install those embedded type of copper features into the board, you need something that while it's going through that copper, that cycling, that copper doesn't cause cracking or fracturing of the material, which is something that you would have to worry about using a polyimide or ceramic type of material. And so this is an area where this material excels and addresses that cracking issue. Under high voltage, CAF resistant conditions at 1500 volts, I mean, what we're seeing now is voltages in the 400 to 800 range, but there's discussions about even operating at up to 3000 volts for these fast charging systems. And so that's an area of discovery that we still have to work on, mainly because the systems to test the material up to those levels is non-existent for the most part in the industry. And so one of the things that also is a concern with these types of products is, what's the highest temperature they can operate at? Well, you all typically is limited to about 150 degrees C with some of the newer materials, but operating temperatures, as I mentioned earlier, are going to be higher than that on a cyclic basis. So this material has been tested, and we'll go through some of that in a little bit, at much higher temperatures than 150 MOT or RTI rating.
And charging speed is something of big interest, yes, in both the manufacturers and the customers of EV vehicles or electric vehicles. Yeah.
Yeah, that's correct. That's correct.
And that is one of the great entree to this slide. It's one of the design basics. It's one of the things that they're looking for. Also power distribution, again, heavy copper, some of the things that polyimide doesn't do well, even though thermally it's pretty good. It has its limitations.
Yeah, so one of the things that's problematic in these electric car designs is the interconnectivity between the two systems. You have the charging system, which you have to take the energy and put that into the charging cable and then connect that to the car. And so those connections where you're taking very high voltage, high current systems and trying to connect those to the lower voltage, lower current systems in the car. And those connections, either lugs or coils and things like that, those get very hot during these processes where you're charging the car. And so the materials have to be well suited for those types of environments. And when you're charging a car, also you're increasing that the fields around those high voltage components, which tends to lead towards CAF problems if you're not designing with the type of material that is very CAF resistant. And so this type of material is really important in these types of systems, so that you're not waiting for your car to charge for a half an hour when you're on a long road trip. And so that's one of the areas that the industry is trying to address, is minimizing that time between when you do charge, between stopping your car and getting that car on the road again with a full charge.
Yeah, so there's other applications for material in this space. And again, this material is very different than epoxy and polyimide and some of the other resin systems out there. So the resin chemistry is different. It cross-links differently. It isn't unknown. I mean, it's been used in composites. If you've flown an aircraft, any modern aircraft, you've probably been around this material or this family of resin system. But there's a lot of other applications as well with some of the things that this material can do.
Yeah, that's right, Chris. So one of the other areas that we're exploring is the downhole drilling opportunities. So for many years, downhole drilling, some of the only materials that have been capable of surviving in the harsh environment is polyimide materials, which polyimide materials are obviously very costly, but they're also very brittle. So you have a material that has to be able to withstand extreme heat, has to endure a lot of vibration without fracturing. And obviously cost is important as well. So this is another area that we've seen a lot of initial interest for those who are building printed circuit boards that do go into downhole drilling and downhole measurement equipment for mining raw materials, infrastructure, roadway, and of course, fracking oil and gas. So it's another whole industry that we think is really going to embrace a material like this.
Yeah, and anything that can withstand those types of applications, but is suitable for standard multi-layer constructions, just makes it easier to design with. It makes it easier for the fabricator.
Yeah,
Go ahead.
absolutely, Chris. So here, we're talking a little bit about some of the ruggedized military aerospace applications, and again, the material we're talking about here is a material that would compete traditionally with the materials that were polyimide based. And one of the things that is probably the biggest deal here is, we've actually seen over the years where designers really want to use, let's say, a 2 or 3 ounce copper in a polyimide application. And due to its inherent brittleness, that presents a real challenge. And with a traditional polyimide type material, what you end up with in those heavy copper applications is you end up with these large clearance areas where you're filling all those clearances with this polyimide resin. And when you go drill through those clearance areas, you end up with fracturing. And we've actually seen a lot of cases where a designer really wanted to use 2 or 3 ounce copper, but because of the fracturing, they've actually they've had to design out that heavier copper, which really isn't what they wanted to do. With a material like the IS550H, you can go ahead and design with that 2 or 3 ounce copper because it's much easier to drill. It has a much better fracture toughness. You can actually drill through these clearance areas without the fracturing. So it actually is going to enable the designers to get the thermal robustness that they need in a resin system and keep the heavy copper that they really wanted in the first place.
Yeah, temperature cycling, at these extremes, can be real hard on the material. And, again, something that doesn't, crack or fracture, that's a big benefit. I've seen customers in their design using polyimide for high temperature applications have to add layers because they can't go with a single or fewer thicker copper layers.
Yeah, absolutely. And this material also flows and fills very well, which again, we can sort of tie that into this next slide here, Chris. So we're looking at some cross sections here from thermal shock. So we see a couple of different FR4s. To the left, we see a traditional FR4 and a halogen-free FR4 on the left with thick copper. And to the right, we see the IS550H. And typically what we see when we do this type of thermal shock on a traditional FR4 or traditional FR4 type halogen-free material is we see cracks. We see a lot of cracks. So you can see those in the red circles there. When you take the IS550H and subject it to this same type of testing, you don't see those cracks. So you're able to go through these harsh, punishing thermal cycles for many, many cycles. In this particular case, it's 1500, and you don't see the cracks. Again, that's because of its superior fracture toughness.
Yeah, that copper bus bar in the lower pictures, that's pretty thick.
Absolutely. Yeah, and we've seen so far with this material, we've done some tests up to 6 ounce. But the heavy copper is traditionally very difficult to work with.
Yeah, that just as a side note, we've done a webinar on copper foils. That's a hot topic in the industry, no pun intended. But a lot of different options for copper exist today. Both the thicker coppers, rolled annealed coppers, low profile. So if anyone has interest in that, look up our webinar on that. But this is an important topic for everything from signal performance to current carrying capacity. We're even seeing some drives towards a copper that's in between 1 and 2 ounce because of some of the higher power chips that are out there, higher power devices. So good segue into this one because high power delivery, the rack servers, other things are great applications for this material. And I know Michael, you've seen some applications like this out there. I know you've worked with some of our customers on some of these boards.
Yeah, definitely. One of the areas that we're looking at in particular is chip testing systems are commonly used where they cycle the materials up to 90 degrees or 125 degrees. And these boards will have a certain life cycle that they can be operated at. So for example, you'll want to cycle your chips 4 times up to 125 degrees C. After a while, some of those sockets start to degrade and they fail and they can no longer test as many of those chips. And then after a while, those boards become less and less capable and more of the sockets are degraded and they have to take that board out and replace it. And so this type of material has the ability to it manages and handles the heat much better. And so they can get a lot more cycles out of those boards and the cost is then significantly reduced in those types of devices. So burn-in boards or characterization boards, ATE boards, this material will give them the opportunity to extend the life of the product overall.
Lead-free phenolics, so epoxy-based lead-free phenolics, the more heat they see, they tend to get more brittle too. I mean, that's just the nature of the resin chemistry.
Correct. You know, all polymeric materials are going to degrade over time, but how long that takes is really the key issue here. This material is much slower at degradation over time versus a typical FR4 material.
Yeah, and how it polymerizes is very different than epoxy.
Correct.
So definitely a need for some higher temperature materials. You know, as electronics are finding their way into, and not just electronics, but electrical devices are finding their way into everything. You know, we've talked about electric vehicles. We've talked about some other areas like ATE boards and whatnot. Well, you know, we see medical applications. We see power, you know, green power generation applications, all of which, you know, for various reasons need more extreme temperature cycling than what we see is typical within the typical realm of FR4. And there's no need to sweat because, you know, there are some good solutions out there, this material being one of them. And this material, because it is a different polymer chemistry than epoxy, it has some different properties when it comes to heat.
Yeah, Chris, and this is a good example of how this material handles the heat in the current carrying capacity. Obviously, with fast charging systems, you're going to try to push as much current through your system as you can to be able to get that product to help charge your vehicle much more rapidly. This compares some typical FR4 materials to the IS550H, and this is really a result of the thermal conductivity of the material. Typical FR4s are about 0.35 watts per meter K, but when you look at this material, you're talking about a 0.7. So it's almost double the thermal conductivity, which allows this material to move heat away from the devices and reduce the amount of energy that remains near the components and allows you to be able to get the heat out of that material more rapidly.
You know, I've talked to some customers about going to thinner cores, so the ground plane can also help with the heat sinking away from the power plane. And I would think that this material would be a great option for that over FR4.
Yeah, you're correct. It would allow the material to, you know, the laminate's not a particularly good conductor of the thermal energy that is in the PCB, and so this material actually will move energy through the material much more rapidly into the copper, which is obviously much more thermally conductive. So you can get the energy and the heat out of that board. That heat and energy that is dwelling in a particular area, that's what's going to degrade the material and reduce the total lifetime capability of that particular PCB.
So you guys have worked with some, you know, very large OEMs, especially for the EV market. And there was a test program or test consortium to get the properties that are needed. So tell us, Steve, tell us a little bit about the HELP project that you worked on with these OEMs.
Right. So there was an industry consortium based in Europe, heavily based in Germany, that was called the HELP project. And that had a sort of a long name to it. It's called the Reliable and Cost-Effective High Temperature Electronics for E-Mobility based on printed circuit boards made of high temperature resin systems. So it was a kind of a long name, but the short abbreviation was HELP. And what this was doing was, the consortium, which consisted of people like Bosch, Continental, Schweitzer, and Isola, and a number of other participants, this consortium identified the trends that were developing and where they saw this industry going in terms of electric vehicles in the future. So they took a look at what was available in the market at the present day and determined that they needed something different in order to move forward. So they started looking at things like high pressure cooker tests, higher maximum operating temperatures, embedded processing, solder joint reliability, extreme CAF testing, high temperature storage, and of course thermal cycling. And so a lot of these attributes were identified, and what they found out was a lot of the existing materials, like typical traditional epoxies or phenolic epoxies, just were not able to cut it, and they needed to work with someone to develop a new resin system, and that's where Isola came in. And I can tell you that initially we did have multiple resin systems that we were working on to try to develop a solution. And in the end, there was only one resin system that was able to meet the requirements identified and pass these tests, some of these that you see here on the screen, and that was the IS550H. So that's really where IS550H was born from this project through all that work. And from there, Isola commercialized it or began the commercialization process. And today we do have the fully commercialized IS550H. But again, this is where it all started with that HELP project.
So this IS550H, as Steve mentioned, it's commercialized. There's a lot of good data on it. These are the numbers, on the far right, and it's comparing it to some pretty well-known materials that are out there. It is halogen free, so for green applications, it's totally suitable. It's a high TG material. I guess you could say it's one of the highest, if not the highest TG material that's not polyimide or a polyimide blend. And again, this resin chemistry is very different than what has been traditionally used in PCB, but more common in the composites industry, areas where there is extreme temperature cycling and they need material to stand up. We can also provide more detail with the technical data sheets that you could either reach out to Isola or Insulectro. We can get you some more data on that. The DKDF charts, all the usual sources for information on the materials. So CAF testing is probably something a lot of folks have heard of, or a lot of people are familiar with. Conductive anodic filament generation is something we all don't want to see in a PCB. And that can form in gaps or spaces with the material. If the material isn't fully wedded to the fiberglass, that could be a pathway. And then if you have electrical bias, it can cause an issue. And you can see this, I think the IPC testing, help me out, Mike, what's the IPC standard testing? I know a lot of customers, a lot of OEMs are looking for 100 volts, but the IPC testing is even lower, right? Is it 10 or 20 volts?
Yeah, you're right about that. So those types of tests that are in the IPC or even some of the common industry testing, like the HDP user group testing, those are typically, voltages at 100 volts or less. In addition, they're really straight whole wall to whole wall gap evaluations, where the concern here with these very high voltages is not necessarily whole wall to whole wall. They are Z-axis CAF failures. How much dielectric do I need between my two conductive layers to be able to ensure that this is going to have a long life in the field on a car? I mean, you're looking at a design target of 20 years operational functionality. And if you have CAF failures when you put these high voltage systems in every year or so, you're going to be spending a lot of money swapping out boards and cars. And so you need to have a material that's tested at much higher voltages to be able to tell user of this material, the OEM of this material, that in an accelerated life test, we can see that this material will last X number of years. And without that information, it's really difficult to predict the capability of the material. And so with this product, IS550, there's been multiple CAF test vehicles, and there has been several applications at both 1,000 and 1,500 volts where we've tested the material, like this example here, and looked at the thickness between the biased pairs of conductors in the board. And so this material actually behaves very well. And we see whole wall capability is also improved by this resin system. And because of the capability to wet that glass to resin bond that is the common location of failure. And so for this type of material, these types of applications, really the primary issue is Z-axis, and then secondary is the whole wall to whole wall. And this 1,500 volt CAF test shows some very excellent capability on these types of test vehicles.
Yeah, high adhesion combined with fracture toughness, those together would lend itself very well to a CAF resistant material.
Correct.
So again, supporting data, for what Mike was talking about with this material, and certainly if you guys need more detail, we can provide that. But very, very impressive numbers on the CAF performance.
Yep, certainly. I mean, these types of tests definitely show us how this material works. Typical CAF conditions are 65 or 85 C at 85% relative humidity, and typically 100 volts DC. And so we typically only run up to 1,000 hours, and these are running up to even longer periods of time. And I expect not only the voltages to increase in these types of test vehicles, but also the number of hours required. So we're going to see more CAF chambers that have this high voltage capability being created and developed in the test capabilities of various labs. In the various laminate suppliers, Isola is currently capable up to 1,000 volts DC. As far as I know, Chris, the only lab that's capable above 1,000 volts is one of the labs in Microtech lab in Asia.
Yeah, that's as far as I know as well. When customers come to me and they say they need something for very high dielectric withstanding in the Z-axis, my best recommendation would be a polyimide film. But this looks like a great alternative for those applications as well.
Yeah, exactly.
So HD Pug, which they don't like to be called HD Pug, but the high density users group, they do some pretty good testing for the industry. And Mike, you guys have worked with these guys on this material and have done some testing.
Yeah, this is a standardized test vehicle that we've adopted for material development. And so we do build, IS550H has been built on this. It is one of the most robust materials we've ever tested with regard to this test vehicle. It also has excellent CAF performance. This has 16 mil and 20 mil spacings on it, but this material passed that testing with ease. It also thermally, because it's a halogen free and its resin system basis is a very high temperature capability. All of the coupons that are on this board pass relatively easily for this type of testing. And so one of the things that we're currently working on is developing test vehicles that look at the Z-axis gap. And so there's ongoing work for capability, but this is our standard capability board here that we use for evaluating materials. This is some of the IST testing. And so thermal cycling, this is one of the areas that people are most concerned about. And so this type of testing is critical to understand with regard to how this material performs. And so this test here is just a room temperature to 150 degrees C cycle testing. And so it kind of simulates kind of some real world type of environments. But what's really interesting about this particular material, we ran it at 150 degrees C, and then we thought, well, let's crank it up a bit. Let's turn the knob up to 11 and see what we can do if we cycle from room temperature to 190 C. A lot of customers, OEMs, they want to see this done to 100 cycles without doing the 150 C cycles first. just do 100 cycles, but we ran this material for 500 additional cycles and it passed that testing. So this is really to demonstrate the thermal cycling capability of the material. And this answers the need of, if I'm turning my system on and off over and over again for thousands of cycles, what is this material going to do if I put it into my design? I think this addresses that particular need pretty well. It gives you a really good understanding of how this material performs. If you put this an FR4 in this same test program, it would more than likely fail, especially when you're going up to 190 C, which is well above most FR4 materials TG. So this is just some of the information about the types of testing that we do. It really describes the CAF test conditions on the typical industry networking and communication type of test vehicle. And pass criteria is pretty simple on these materials, but with the designs that are going into automotive applications, you're talking about, 0.2, 0.3 is starting to be a pretty common spacing, the whole spacing in these designs. And so you got to take a look at how the material performs in a CAF condition where you have biased pairs that are much closer than the typical 16 mil or 20 mil whole wall to whole wall. So the IS550H has passed both the 16 and 20 mil gaps, which is a very uncommon case. The 16 mil was developed in the board originally to cause failure. Well, the material also passed the 20 mil gap. So this material passes both of those, and that's pretty significant capability for a material.
Yeah, so not only has it passed some of the new tests that were developed around the HELP project, it also passes the standard tests at higher levels in many cases.
Yeah, exactly.
So this just kind of sums it up. Hopefully we have some good questions that our panelists can answer for you guys. But this is a summary. And Steve, why don't you just wrap this up for us, and then we can get into the questions.
Yeah, really. So thanks, Chris. So just in summary, thermal cycling resistance, obviously some numbers that are, well beyond what we would see with a traditional FR4 material, negative 40 C to plus 160 C, 2000 cycles, hot storage testing. We've talked quite a bit about CAF testing. So obviously, we know the CAF capabilities of this material are far beyond traditional FR4 epoxy materials. And then excellent fracture toughness, and that's something to keep in mind, especially as it pertains to some of these heavier copper polyimide applications. Very good flow and fill out of this material, so it does a very good job with the heavy copper. And the great thing about this for a PCB fabricator is it processes very similar to an FR4. So you'll get polyimide-like performance, but the processing is nothing like a polyimide.
Great. Okay, Ron, do you want to open it up for questions?
Yes, thank you. First of all, great job, guys. That was really very well done. So we've got a couple questions here that were sent to me here to, one of them I think we've covered here already, and that's had the halogen-free question, which was a yes. We have a question on processing. So because of some of the material attributes, although it may be like FR4, are there anything that the fab might be concerned about either in lamination, drill, or hole prep?
No, Ron, when it comes to lamination, drill, and hole prep, this material processes very similar to some of our other high TG FR4 materials. There's really nothing special about it. We're not going to tell you need to have any sort of, advanced plasma process or anything like that. Every printed circuit board fabricator has processing set up a little bit different from one place to another. So there might be minor adjustments from one site to another. But no, there's nothing. This material is nothing like some of the other materials you've seen where you have to do something significantly different, or you need to laminate at a temperature that would require you to use Skive Teflon or something that would you would not normally use. So it is truly what we consider to be traditional PCB processing.
Very good. Question here. Is this material available on all standard prepregs and cores?
We do have a full complement of offerings. So, the answer is yes. As you know, Ron, with all of our materials today, we do have differences from one resin system to another. So if you're looking at, I-speed compared to 370HR compared to polyimide, we don't always have all the same offerings on every resin system, but you will find a full complement of offerings from a 2 mil core on up, and a full complement of pre-preg offerings as well. So we're not limited to just, let's say a couple of different glass styles or something like that. You're going to see a full complement of offerings.
Very good. So here's a question on the UL and IPC. So UL, anything unique there? And what is the IPC slash sheet for this product?
It is IPC slash sheet 140, which is a brand new slash sheet. So, when you mention that to somebody, they might want to open up their IPC book 4101 and look. They won't find it there. So this is a slash sheet. We have proposed this to IPC. They have accepted it. So we are in the process of getting all that work done. So it's a slash 140, and I would say it's pending. So we are producing this material today, and we are certifying it to that pending slash sheet. And this is something that we expect to have fully completed through IPC this year, but it is going to be 140.
Very good. And on the UL, I think we touched upon that. That is a VO rated material, obviously. It
is. And if customers or designers take a look at our website, there is a link to our UL file, and they will see that the IS550H is already there.
All right. Another question. So many of Isola materials are hybrid compatible. Is this a product that could be used in a hybrid construction with another or a different material?
Yes, Ron, it definitely is. And one of the things we're doing is, this is a halogen-free material. So typically, if a customer were interested in using a material like this, they would want to couple it with other halogen-free materials. So one of the things we are doing is running this along with one of our new products, which we're not talking about today, but that's the TerraGreen 400G, which is also a halogen-free material. And yeah, it's definitely hybrid compatible. And we'd be happy to talk to folks about that.
Very good. Sounds like we might have another form coming up on TerraGreen 400G.
Yeah,
that sounds exciting.
To talk about it.
All right, and we've got a question here. Do you have data on how many lamination cycles this product can withstand?
Yep, we have done some sequential lamination, and I believe so far, and Michael, you can tell me if you know of anything more, but I know we've done, I think, up to 4. There's no reason to believe it wouldn't go farther, but yeah, we can specifically address that further as we go forward. But it's definitely compatible and capable of multiple sequential laminations.
Yeah, and if you're familiar with OEM testing, where you're looking at cycling with HDI type structures, some testing has been done on that material early on. So that's the kind of testing that we're working on, expanding and trying to get some additional data on as well.
Very good, Mike and Steve. That was the last question that we have, at least on the board here. Anybody else have a question that we could help? Well, I'd say you guys covered it very well.
Thanks, Ron. We really appreciate the opportunity to talk to everyone today.
Yes, definitely. Thank you so much.
Great. Well, thank you, Isola. And thank you, Chris Unrath. So in closing, let me just say once again, thank you all for your attendance. We know that everyone's time is valuable. And please connect with us for future topics that you and your organizations want to learn more about. And you can reach us at, and you can see it here in the last slide, OEMforum@insulectro.com. We welcome your ideas, views, and questions. And please be sure to follow us on LinkedIn to stay current with our industry news and supplier highlights. And lastly, I would just like to let everybody know that coming up on the next OEM Forum, we'll be talking about Indubond, an X-Press 360. It's a lamination press manufactured by Chemplate Materials out of Barcelona, Spain. They're a world-class supplier teaming up with a world-class manufacturer teaming up with a world-class supplier. So come hear more about the next innovation in multi-layer lamination. All right. So with that, again, I want to say thank you, and everyone, please have a great day. And again, thank you for joining.
Thanks, Ron.
Thank you, Ron.